Hello everybody, my name is Elias. I work at the Dfinity Foundation as a software engineer. We're probably the largest R&D corporation in crypto at the moment. And today I want to talk to you about Ethereum and ICP and how you can connect those two. So first, I would like to start with explaining the internet computer in general a bit, because I assume not everybody is familiar with it. And then in the second part, we will look at how to integrate it with Ethereum, and I'm going to show you some code, what you can do. So what is ICP? There are many definitions, and I've picked two that I like the most here. So you can think of ICP as a decentralized and permissionless cloud that's built on blockchain technology. So the internet computer really behaves like a decentralized cloud computing platform, basically. And another way to look at it is that ICP aims to extend the internet, and it does that by giving the internet the capability to directly run software. You know, usually you have to go to some centralized cloud provider and they will run your software, but there's no way to directly build on the internet, right? Because the internet is only there to connect you with other servers, and it can't run software directly. Now, in 2009, the first Bitcoin block was produced, right? And today, Bitcoin is referred to as digital gold. Then a few years later, in 2015, we had Ethereum that gave us the capability to write smart contracts. And then in 2021, the internet computer mainnet started. And you can think of it like a third generation blockchain, with Bitcoin being the first generation, then Ethereum, and finally the internet computer. And that's important because even though Ethereum has some smart contracts, it's still quite limited in what you can do. You know, it costs a lot of money to store data, transactions take quite some time to be final. But the internet computer really tries to overcome these issues and allow you to host all software on-chain. Now, let's take a look at the architecture of the internet computer for a bit. So at the base layer, we have what's called nodes, and those are run by independent node providers from all over the world. And that's quite different if you compare it to Ethereum, right? On Ethereum, we have about 70% of the nodes running on AWS and other centralized cloud providers. So whenever AWS or Google Cloud would decide that they don't want to run Ethereum nodes anymore, they can just snap with the finger and 70% of the network would be gone. And that's, of course, not desirable. So for the internet computer, we really have our own nodes that are operated by independent node providers around the world. Now, those nodes are special high-performance hardware, so not any machine can become a node. We have quite high requirements. That's because we want to have a uniform blockchain with very capable machines, such that we can host all the software that is out there. And that wouldn't work if we have, you know, some laptops being nodes or something. That those would be just too slow. Now, those node providers operate from different data centers around the globe, and we really make sure that those are independent ones and they don't belong to big tech, so that it's really resilient to, you know, to some nodes going down and to have the redundancy around the globe. Now, on top of those nodes, we run what's called the Internet Computer Protocol, or ICP. And what it does, it combines several nodes to form what we call subnet blockchains. And with this architecture, the internet computer can scale infinitely. So if more users come online, we need to host more smart contracts. The governance system of the internet computer can autonomously decide to create new subnets, and those subnets can then host more smart contracts, and so it really scales horizontally very well. And to the user and to the developer, you don't really need to care about those individual nodes and subnets. So to you, it really appears as like one uniform virtual computer. Now, the third layer that I'm showing here is kind of this this cloud space that is created, where users can then run their code in. And now if we compare this to Ethereum, those numbers are from a few days ago, but the proportions don't really change that much. So I think, you can really see Ethereum can process about like 16 transactions per second. On the IC, we can have over 1,000, multiple thousands, with the peaks being even higher. And again, if we would see more demand, we can just add more subnets, and that's how we can scale infinitely. Also, transaction finality is around 1 second on the internet computer, and the transaction cost is insanely cheap compared to any other blockchain. And storage costs also, orders of magnitude cheaper on the internet computer. Now, on top of this cloud environment, run what's called Canister Smart Contracts, and they're an evolved form of normal smart contracts you might be familiar with from other blockchains. And those make up the main building blocks of the internet computer. And they're really not like traditional smart contracts. So they can host, for example, up to 400 gigabytes of data. And you can really have any kind of software running in there with almost no limitations. So, for example, we have social networks that run entirely on-chain. I will show you one in the demo. And also just recently, we have demoed that we can do image classification on-chain. So that means you can even run neural networks inside a smart contract. And that's just unheard of in any other blockchain. And finally, canisters also can serve frontends to you, and you can interact with them at web speed. I will show you this in a second. So you really won't know that you're interacting with a Web3 environment on a blockchain. It really feels like you're just browsing Web 2. Now let's take a look at some key capabilities of Canister smart contracts. So first of all, you can use any language to write those canisters as long as the language can compile to WebAssembly. And the canisters can then execute this WebAssembly, and they can also store data for you. So for example, we have Rust, we have a JavaScript framework, we have a Python framework, and we also have our own programming language called Motoko that's specifically designed for the internet computer. And you can use a bunch of languages to write smart contracts. Now, another thing that's different from, for example, Ethereum is that we have what's called a reverse gas model. So, on Ethereum, every time you want to make a transaction, you have to attach some gas to pay for the computation. And on our smart contracts, that's kind of flipped around. So the canister is paying for its computation itself, and the users don't need to worry about gas fees or anything. They can just use the contract and the developer or the community takes care of charging the canister with enough cycles. So those cycles are kind of like gas fees on Ethereum, but it's just that users don't have to pay them, but the canister pays it themselves. Now, canisters can of course also hold tokens, so they can hold our native token ICP, and we also have our own token standard ICRC1 that's similar to ERC20 on Ethereum, and they can transact with these tokens, hold them, everything you would expect. And we also have, since a few months ago, we have also Bitcoin and Ethereum, and soon we will also have other ERC20 tokens like USDC or you name it, that you can use in your canister and transact. And those coins are created without a bridge, so you can think of them like digital twins of Bitcoin or Ethereum, and we use what's called HTTPS outcalls and chain key cryptography to make sure that we can have these tokens without a lot of trust involved. Because normally what other crypto projects do is that they have some bridge, but that always involves some trusted party. Even if you have things like multisig, you still need to trust a few parties. And here the entire code is open source, and it's really just smart contracts interacting with each other, so it's much more secure. Now here I depicted how the topology can look like. So you have different subnets. All of those subnets can communicate securely with each other. They can all produce blocks on their own. And we have one special subnet that kind of controls the topology of the entire network. Now, let me summarize some of the key things that I love about the internet computer. So first, as I've said, we have our own data centers that are operated by independent node providers around the world, which makes it much more decentralized than if you compare it to Ethereum. We also have community-owned services. So, for example, OpenChat, that's one of the dApps that was built on the internet computer, recently had a kind of like a crowdfunding where users were able to give some ICP and get the governance token of OpenChat in return. And so now those services are really controlled by the community through these tokens. Now, other blockchains sometimes have a hard time upgrading themselves, and that can lead to forks if the community doesn't agree. That's also different on our blockchain. We have autonomous upgrades because we have this special subnet, and everybody who holds ICP can participate in the governance and can decide on the network topology and on all software updates that our blockchain does. And once such proposals are accepted, the update happens autonomously, the code gets executed, and forks can't happen. We also have what's called full stack decentralization. So as I've said, you can have front-end and back-end on-chain. You will see that in the demo. And we have chain key cryptography. We've had this for, I think, a year. Other blockchains are slowly getting into it as well. And this allows you to basically hold assets from other blockchains in our smart contracts. And if you combine this with the capability to make HTTPS outcalls, this allows you to call normal websites from Web 2, get the data, and process it in your smart contract. So this is really phenomenal. Now, I would like to give you a quick demo and show you some dApps that have been developed on the internet computer. So first, let's start with the dashboard. This is kind of like our block explorer. But you also see the network topology here. You can see we have nodes all over the world. We process around 5,000 transactions. And our transactions are also much more capable than Ethereum transactions. So here we have the Ethereum equivalent as well. So our transactions are roughly 80 times as powerful. You can also see we produce around 41 blocks per second. And recently we surpassed 3 billion blocks. You can see here how many cycles are being burned. That gives you an estimate of the usage of the network, because all the smart contracts burn cycles when they are running. And here you have some other statistics. You can see we have around 500,000 smart contracts. You can also look at the transactions of ICP and other tokens. So that's that. Then as a first step, I would like to show you the OISI wallet. So here you can have our ICRC2 tokens. Those are kind of like ERC20 tokens on other chains. And, oh, I see something went wrong. That is just the internet connection. So here you can receive your assets, and they are all natively on our chain. But as I've said, we also support cross-chain calls. So you can also hold Ethereum assets in here. So users can receive some Ethereum, you can integrate it with MetaMask. So here, for example, you can directly receive funds from MetaMask. You can send them over to the Canister on the internet computer. And that allows for really a seamless experience for users when it comes to cross-chain calls. Now, we also have entire social networks on our blockchain. So here, for example, this is Tagger. That's a social network on the IC. And you can see, if I refresh the page, you can see it's really fast. Remember, this is all running on-chain, the entire front end and back end. So all the assets you see here, they're all fully on-chain. Users can comment, like, everything. Now here, that's another tab. It's called OpenChat. I've mentioned it before. This is completely owned by the community with this governance token that they have, chat. And again here, we can just write a message here. And that message is now sent to the Canister, and all the users will get push notifications in real time, all on-chain. Now, we also have what's called the network nervous system. That's like our governance system. And so, for example, here I selected OpenChat, and you can see all the different proposals that OpenChat has currently open. And the community can now go there and vote on these proposals. So, for example, if they want to transfer some treasury funds, there's a proposal for that. And you can see most of the people accepted that for now. And if it gets accepted after the deadline, it will autonomously transfer those funds. And also, smart contract updates happen like that. So the users will be able to verify the changes. From GitHub, for example, they can see the code that went in, and they can give a thumbs up or down if they want to accept that. And so we have a lot of community projects here that raised millions of dollars in this crowdfunding scheme that we have. And also the internet computer itself has such a system to upgrade the node topology, to bring new nodes online, or to upgrade the host operating system that's running on our nodes. All right, now let's go back to the slides. So now I think I've shown you some of the capabilities and what dApps we have on our blockchain. So now let's go to the second part, how you can integrate this with Ethereum. So we have a special Canister smart contract, the EVM RPC Canister, that can talk to EVM-based chains, and it can sign native transactions and hold funds. So this means we can get a public key, then we can derive an Ethereum address from it. We can advertise this Ethereum address, people can send money to it, and then when it comes to sending that out, we can just sign the transaction with our chain key cryptography and send the funds. So our smart contracts basically have access to public and private keys. And as I've mentioned, we also have those twins, CK-ETH and other CK-ERC20 tokens that live on our chain, but they're always backed one-to-one by the corresponding asset on Ethereum. And that gives you really cheap transactions. So now, what are some of the benefits that you get when you integrate the IC and Ethereum? So first of all, you can have everything on chain, all computation, all assets, everything. And this makes you much more resilient to some outages, or it frees you from big tech. For example, Uniswap has their front end on AWS, but only tiny parts of the backend, like when it comes to token transactions or swapping tokens, that's happening on chain. But here you can really move the entire stack on chain. Then with our twins, you can have low-cost transactions. That's something that users would really love. Also, our transaction fees are constant. They don't change depending on the demand. And what you can also do is you can offload heavy computation to the internet computer and use it like a side chain. And then once you're done with the computation, you can load the data back into the Ethereum smart contract. It also allows you to get rid of oracles and bridges, because you can make calls to the internet directly from a Canister, and you don't need any trusted third parties managing that. And finally, as I've shown you, for example, with OpenChat and various others, you can give away control of your dApp and really create a DAO, a decentralized autonomous organization that can control your application. They will have the ability to upgrade the canisters when it's needed. And yeah, you can have real decentralization and community ownership. Cool. Now, I want to give you a demo of the Ethereum RPC Canister. So let's open VS Code. So here I've created a project. You can use that later for the hackathon to get started. I've integrated it with Gitpod and Codespaces, and you can also do it locally on Windows. It doesn't matter. We use Docker containers such that it runs on all platforms. You don't need to install anything, so I highly recommend you check out this repository afterwards. And this repository consists of two smart contracts, front-end and a back-end smart contract. The front-end is just React, and the back-end is written in Rust. So let's take a look how it looks like. So here, this is my application, and the backend here can natively talk to other chains through RPC providers. So here, if I click on Get Latest Block, it will contact some Ethereum RPC providers and load the data back into the smart contract on the internet computer. And now you can see all the transactions. You see the block number. Let's see if it's really live data. So you can see it, block is 30 seconds old. So you can really, in real time, process this data. So let's take a look at the code, how this works. So here in lib.rs, this is the main file for the backend smart contract. And here I expose an update function. It's called getLatestEthereum block, returns a block. And here I can specify the RPC providers that I want to use to fetch the data from Ethereum. So I'm using Cloudflare here, but you can also add some more if you want more security. So what this will do is it will fetch the data from those two RPC providers and then check if they agree with each other. So you might want to do this because only relying on one RPC provider might be not really trustworthy. So here you can have a list of RPC providers. Then, since the Canister needs to pay for its own computation, we need to attach some cycles, or Ethereum gas, basically, to our call. And then we call the EVM RPC canister. That's another canister that's specially designed to talk to other chains. We just give it the list of RPC services. We say we want the latest block. You could also, of course, get a specific block number. And then we attach the cycles. Now, for the cycles, I just provided some huge number here because the cycles that are not used are actually being refunded to my account. So that's also not like on Ethereum. The miners would be happy if you do that. They will just take it. But here we can really get them back. And also the prices don't fluctuate. They're constant. And yeah, so this is the call I make to the RPC canister. And then I get back this get block number result. And I have a match statement here that looks at the results that we got from the RPC providers. And I can get a consistent result. That means that all of them gave the same answer. And then that result can contain the block that I wanted, or it can contain an error if I malformed the JSON or provided some wrong parameters. Now you can also get an inconsistent result. That would be if Cloudflare and Alchemy provided me with different results. Now you can also talk to other RPC providers. So let's do that. Let's make another RPC service. And this time we're going to use custom and not Ethereum mainnet. You can see we also have here the Sepolia testnet if you want to just test it. But we're going to use a custom one. And it asks you for the chain ID and then some services. So I recommend you look at chain list. There you can see a bunch of EVM compatible chains. So I don't know, let's choose Optimism. So chain ID is 10. So we provide 10 here. And services, we want a vector of RPC providers. And so let's create them, RPC API. And here I just need to provide a URL and optionally some headers. So we don't care about the headers for now. And now we just copy one of the RPC providers here. So RPC providers give you information about the latest block and transactions. Let's choose this one. Has 2 check marks. Paste it in here. There we go. And now you could also add more RPC providers. You should do that if you want to deploy to mainnet to have more confidence in the results you get. And now we can comment this one out. Now I can redeploy the backend canister. I do that with DFX. That's our Swiss Army knife tool that does everything. If you want to develop on our blockchain, it can deploy canisters, top them up with cycles, everything. So let's redeploy the backend. So now. And now we can go back to the front end. Can refresh the page. Now we get the latest block, and if I didn't make a mistake, we should now get optimism blocks, right? So let's see if that makes sense. Let's go to the optimism block explorer, paste in the block number. It looks good. So this block is 15 seconds ago. And yeah, so this is how you can talk to other chains. Now, I've also prepared some functions here, how you can get a public key. You might want to do that if you want to send around funds, right? That's important. It's very simple. You can see it's like one function call. It gives you a signature, and you can, it gives you a public key, and you can use it to derive addresses, whatever you want. Here, another function call, again, very simple. One call, and you can sign transactions. Then you need to send them over to an RPC provider, and they can process your transactions. Right. So let's go back to the slides. So I highly encourage you to check out our hackathon track. We have the highest prize pool of $20,000. And if you want to create a seamless cross-chain experience, I think the Internet Computer is really the best option that you have. So I have some QR codes here. You can take a picture and then scan them later or now. So we have the ICP track info. You can find all the requirements and more materials. You can join our mentors group on Telegram. You can ask some questions. I will be here today as well. Or you can join our dev Discord. And finally, that's a link to the repository that I was just using, where you can get started within a few minutes. You don't need to install anything, and you can start coding today. Thank you.